This is Free Range Digital Design Foundation Modeling, Chapter 12. This is the second lecture, and we're talking about signed binary number representations. And we had been studying diminished radix complement, signed magnitude, and radix complement, and with the emphasis on radix complement, which was 2's complement. Now, the interesting notions of these things you always have to understand and take with you in this lecture here, as well as bit extensions, which is something you always have to do with numbers. So once again, signed numbers, leftmost bit's always a signed bit in the representations we're working with. If the signed bit's set, which means it's a 1, it's a negative number. Otherwise, the signed bit is cleared and it's a positive number. So the important thing to realize here is the number ranges associated with a given number of bits. The number of bits in your binary number is going to determine the number ranges associated with that number of bits. And of course the range is a function of the number of bits. But what's interesting here is the signed magnitude and diminished radix complement have a little bit different representation. So we have an example here. There's both formulas, and then I have these are the associated formulas, and these are the associated values with n equals 8. So all these examples use n equals 8. For unsigned binary, the formula is the number range. It starts at 0 and it goes up to 2 to the n minus 1 as given by this formula. That means 2 to the 8th is 256 minus 1 is 255. So this range for unsigned binary goes from 0 to 255. So 0 to 255 is truly 256 numbers, which is 2 to the 8th. Okay, that's a very important fact. I mean, it's kind of zero base, of course, and it makes you think, oh, there's only 255 because 255 is the greatest number, but there's actually 256 because we include 0 in there. Now, what's interesting for the signed magnitude and DRC range here, it's a symmetrical range, and so the idea goes from 127 to negative 127 to 127 for an 8-bit number, and which is symmetrical. Well, the problem is there's 2 representations for 0. Going to create a problem when you're designing hardware to work with it. So, but the important thing is, once again, these are symmetrical. It's symmetrical about 0. There's 255 different numbers that the 8 bits represent, but it has 2 ways of representing 0, which presents the problem. Now, these are the 2's complement or radix complement numbers. So if you look at this thing, the number range is no longer symmetrical. So it has an extra bit on the negative end, extra bit, extra number. So instead of having 2 zeros like it did for the previous ranges, it has 256 different numbers, which is, you can't really make that symmetrical about 0. So what it does is it makes it asymmetrical by giving an extra number on the negative side. So for 8 bits, I have the biggest negative number is 2 to the n minus 1. The biggest positive number is 2 to the n minus 1 minus 1. So this is something you'll get used to. It's not really that hard to memorize, particularly if you remember this n equals 8 example. Okay, the important thing here is unsigned binary. There's actually 256 different numbers. For these 2 representations, there's 255. Two representations of 0, which is problematic. For signed binary radix complement form, there are truly 256 different numbers, not symmetrical about 0. I always like to say, like, this range is essentially the same as these other 2 ranges here, but now they're kind of sort of centered around 0. One common thing you do, binary numbers working with hardware, is you need to extend the width of the number without changing the value of the number. Probably done it a million times before with decimal. 47, what you do is you stuff a bunch of zeros on the front end of it, or if it's has a fractional part, you put stuff zeros on the other end of it to extend the width of it, I guess. Okay, so not a big deal. You never really thought about hardware when you're working on decimal, but now we need to consider hardware, and what we do here, we typically need to extend the data widths of these things. So I'm only going to talk about unsigned binary and signed binary. The idea here is for unsigned binary, it's just normal stuff. You just You add a bunch of zeros, which I call zero extend here. But for sign binary radix complement form, it needs to be sign extended, which is a little bit different. What I need to do is convert these two unsigned binary number values to 10-bit numbers. So there's 1, 2, well, let's see, 1, 1, 1, 0, 0. That's 5, 6, 7, 8. It's an 8-bit number. I'm going to add 2 bits on the end of this thing, and suddenly it's a 10-bit number. Okay, so this is a 1, 0, 1, 1, 0, 1. That's 6 bits. If I want to make it into 10 bits, I add the other 4 bits to this thing, and suddenly it's a 10-bit number. So this is 0, extending it like you are used to using before. Not a big deal. But now we get to signed numbers, particularly radix complement format, 2's complement format. I need to adjust the width of it, and so these examples here are examples of taking these numbers and extending the width from whatever number of bits they have to 10 bits. So this one's 1, 2, 3, 8. Okay, and there's the 8 bits repeated there. It's a positive number, so I'm going to sign extend it. The sign is positive, which means it's 0. So I'm going to add those 2 extra zeros on the end of it. And that works, and it's increasing the bit width of a negative number in 2's complement format is a little bit different. You don't add a bunch of zeros to it, you need to add a bunch of the sign bits to it, which is essentially what I did here. 0 was the sign bit, I added a bunch of zeros to it, so which is sign extension. So this one is 1, 0, 1, 1, 0, 1. That's 6 bits. I see that's the sign bit is set. I need to be 10 bits, so I add 4 of the sign bits to it, which means sign extension on this. And I truly haven't changed the value of that number. Be careful. If you're working with unsigned binary, you just add zeros. If you're working with a signed number, particularly RC format, you need to sign extend it, not 0 extend it.